Free body diagrams. This is probably the most important skill that you will learn in high school physics and especially in grade 11. I feel like I've said that a lot, but I promise with free body diagrams, these never go away. I know exactly what you need to know when it comes to university physics and even grade 12 physics. Um, I promise you, you need to be able to draw, understand, interpret, and just know everything that there is to know about free body diagrams. These show up in virtually every type of question. And you cannot do dynamics questions without drawing a free body diagram. What this is a snapshot of a specific object that focuses on any forces that are acting on that object at that time. Um, it's a simplified vector diagram. That's what it is. They're just vectors because force is a vector. So if we want to know what force is, what is the net force acting on an object, we need to draw a free body diagram to figure out what are all the forces acting and in what direction. Now, students seem to think that they can solve dynamics problems without drawing a free body diagram. You're wrong, okay? Straight up, you are wrong. You need to you need to start with a free body diagram in order to solve any type of dynamics problems, okay? So this lesson is all about how do you draw free body diagrams. So first step, pick the object that you're going to focus on and the instant in time or the motion that you're looking at. That one's pretty straightforward when it comes to the questions. You'll know exactly, like that's not going to change very much, but you'll know exactly what object you're going to look at. In grade 12, you'll do things with multiple objects, so you'll have multiple free body diagrams. We're not going to focus too much on that this year, but that's just something to keep a lookout for. Draw a box, okay? Everything in physics is represented or modeled by a box. It just makes things nice. You got an object, draw your box, okay? Then you need to set your coordinate system, okay? We always assume that right and up is positive and left and down is negative. But if you want to do otherwise, you can do that, right? You can decide otherwise, and we're going to see a little bit later in this unit how that can change. Really, what the biggest thing when it comes to setting your coordinate system is you want the direction of acceleration to be positive, okay? You can do it the opposite way, but you need to set your direction of acceleration to be positive, okay? It just makes things nicer later on. We'll kind of see, and I'll talk you through how that can change, okay? Now that you've got your box, you know which way is positive and negative, just draw any forces acting on the object, okay? You're just drawing arrows. You can draw things on angles, but you should then split it up into its components just like a vector, so you only really have X and Y direction forces. And I'll show you what that looks like in a second. Once you have all your forces drawn, now you can write your sum of the forces in the X direction and the sum of your forces in the Y direction equations. If this sounds, number 5, if this sounds like a vector collector, that's all it is, okay? It's just a different way of looking at it, okay? But different. Very, very similar, but slightly different, okay? So to start, here we have 3 net force free body diagrams. So if we wanted to look at the sum of the forces for all of these ones, well, this first example, we've got 2 forces going up, 1 force going down, which means we can say that the sum of the forces, and I'll call this the Y direction, okay? Since we know that up is positive, we're not going to change that. We know that we're going to get 20 plus 8, and then we are going to subtract 12, which means the sum of the forces in the Y direction is going to be 20 plus 8 minus 12, which is 16 newtons, okay? Just up minus down, That's all that's happening here, okay? If we do something very, very similar for the second one, except now, if you notice, we're working in the x direction, and we've got a whole whack load more forces. So we can say the sum of these forces, well, what do we have going to the right? We've got 17 to the right, plus 5 to the right, plus 9 to the right, but we're losing 13, 16, and another 16 all to the left, which means in total the net force, the sum of the forces acting on this entire object, is actually negative 14 newtons. And that negative means to the left, okay? That's fine. Cool. Now, if we take these two things and have these two types of forces acting on the same object at the same time, we get question number 3, right? We've got a bunch of forces acting up and down, and then we've got forces acting left and right. So the only way to do this is to say, all right, well, if we start in the x direction, let's only focus on these x direction forces. We've got 45 newtons right, 70 newtons to the left, which means we're going to get 45 newtons minus 70 newtons, which we're going to get a grand total of negative 25 newtons. And again, that negative means to the left. This object will move to the left. Now, if we do something very similar, but in the y direction, well, we've got 50 newtons and 18 newtons going up fighting against 60 newtons. So we can say that the sum of the forces in the y direction is going to be 50 plus 18 minus 60, which is going to give us a grand total of 8 newtons. Positive 8 newtons, which means the positive, you don't need to write it, but that tells us that it goes to the right, which means the net force of this object is both left and right at the same time. Oh my goodness, but I messed up, didn't I? This is not right. This is our y direction. Positive for our y direction means up. My bad. I am so sorry. Right? Left and up. So that thing is going to move at a kind of an angle there, left and up, just like vectors, right? What this really looks like, if we go back, and I don't love writing it like this, but you can do it if you want, right? This is just a vector collector. We've got 45, we've got negative 70, we've got 50, 18, and negative 60, okay? That's all we have here. We've got our y components and we've got our x components, but we are writing out in equations now because we've graduated from vector collectors, okay? Cool stuff. That's how we work with free body diagrams. But how do we actually draw the free body diagrams so that we can get to these equations? Okay. So what we have, right, what we have to do is look at, well, what forces are acting in what direction? So we need to draw a free body diagram for two forces, F1 and F2 pulling right, and F3 pulling left. So if we draw a box, because remember I told you everything in physics is a box. So if we just work with general, we've got F1 and F2 pulling right, and then we've got F3 pulling to the left, which means the sum of the forces in the x direction is going to be F1 plus F2 minus F3. Now we can't do much with that because we aren't given any numbers here, but that's the idea. We've got forces to the left and forces to the right, and whatever the combination is going to be our net force, okay? Now, physics is all about the real world. So there are multiple different forces that you'll see and show up in real world questions, but we've got 4 main ones. Now, the first one is the force of gravity, okay? This is Fg, and the force of gravity is always equal to mass times acceleration. It is always, always, always directed downwards. So if we have a box on Earth like so, okay, we have the force of gravity going downwards, and that force of gravity is always, always, always equal to mass times gravity, okay? Now, so we can say here, if we really want, that this force of gravity is the same idea as your weight, okay? Because it changes based on um, where you are. On Earth, we have gravity equal to 9.81 meters per second squared. On the moon or on different planets, it changes, but on Earth, we get 9.81. Now, one thing about gravity is that you don't necessarily need to use negative 9.81 anymore, because what we would say here is that the sum of the forces in the y direction is equal to negative Fg, because that negative is going down already. So we use that negative in there so that we can just use positive 9.81. If you'd rather just add Fg and then have negative 9.81, it's totally up to you. But I like to look at right minus left, and that negative is the negative of gravity is already taken into consideration when you say that Fg is negative. Okay? That's the first type of force. Second force is the normal force, okay? How I like to call this one, this normal force is the contact force, okay? If you have contact between objects, then you have a normal force, okay? If you do not have contact, like if you're just falling down through the air, you do not have a normal force. This is always perpendicular to the surface, and it stops objects from pushing in on each other. When you're sitting in your chair right now, your butt is putting a force onto the chair, but the chair is applying a normal force to your butt because it's stopping you from falling through and falling into the chair. It's the contact, it's the Newton's third law, opposite reaction force to contact, okay? If you have any type of contact, you must have a normal force. So we can have a whole bunch of different options here. The first option being a box just sitting on the ground, where we can have the force of gravity pushing it down, but we're going to get the normal force pushing it up, perpendicular to the surface. So that's option one. Option two, maybe you've got a vertical wall like this, okay? Where, okay, we still have the force of gravity pulling it down because the force of gravity is always, always, always down. But where's our contact? Our contact is right here with our normal force, okay? Now, in order to keep this box against a wall, we probably need some type of applied force applied to the box in order to keep it against the wall so that we actually have a normal force to begin with, okay? The other option, a little bit more advanced, we might not see it too much here, is if we have two boxes. Let's say we have a smaller box here next to a larger box, okay? Now, both these boxes, I'll call this FG1 and FG2, both of them have the force of gravity is going down, but both of them have their normal forces going up, like so. I'll call that FN1 and FN2, but what we're missing here is this part right smack dab in the middle, where we've got a normal force pushing that way, and then we've got the normal force going in the opposite direction because we have contact between them. Anytime you have contact, be it with other objects or the ground or walls or anything like that, you must have the normal force. Cool. The next one, force of friction. We're going to look at friction a little bit in more detail later, but this is always acting parallel to the direction of motion and always against the direction of motion in the opposite direction, right? Friction never, ever, ever pushes things along. It is always slowing things down, resisting motion. If you have an object falling through air, friction is the force of drag, okay? Kind of FD, force of drag. We're not going to see it too much, but really friction is just anything that resists motion. The big idea with friction is that friction depends on the normal force. Friction depends on the normal force, or how I like to think of it, how much contact we have. There is, right? The more contact you have, the higher the friction is. It's a lot easier to pull a table across a rug when there's nothing on the table versus if your sibling or someone is sitting on the table, right? There's a lot more contact, which means you have more friction. Now, the formula for the force is always, we're going to look at the formula a little bit later, but the force of friction always goes against motion. So let's say we have motion to the right. That tells me that the force of friction must be acting to the left, the force of friction, just like that. Okay? Again, we're going to look closer at friction a little bit later. Now, the last one, again, but not, this isn't an end all be all list, but the last one is some type of applied force. This is an external force acting on the body. Sometimes you push things, sometimes you pull things through a rope, sometimes you have engine applying a power. Literally anytime you have a force applied to an object. Now, if you're pulling through a rope, you might see this as a tension force. Tension is just another way of saying an applied force. They're all the same thing. Now, so we've got two options when it comes to applied forces. If we have a box just sitting on the ground like so, there we go. We already know from previous that we've got the force of gravity and we've got the normal force going on like that. So that's totally cool. But now we have this applied force pulling perfectly horizontal. That's totally awesome. That is all in the X direction, okay? But where this applied force gets tricky is if you start pulling an object. Now, okay, so hold on a second. Let me add in this force of gravity, normal force. That exists no matter what. But if you start pulling an object at an angle like this, well, now all of a sudden we can't do much with angles in free body diagram. We need to split up our force into our components, our X and Y components. So instead, you are going to get FAX and you're going to get FAY in the X and Y directions, okay? And again, we're really good with vectors right now, so that uses trig, and this is just vectors. That's all it is. We need to split up our angled force into vectors. Just like before in relative motion, when I gave you a wind or something going like northeast or at an angle, you needed to take that vector and split it up into X and Y components. This is exactly the same thing. We don't know how to deal with this applied force on an angle, so we need their two components in the X and Y directions. So these are the four forces, the main things that show up. This is not an always list, so don't think that this is the end all be all. But again, this is the stuff that you're going to see over and over and over again. So I'm going to do a couple examples of drawing free body diagrams in the real world. Now, we're going to go over more of this in class. We've done a lot of stuff like this, but we're going to draw these free body diagrams, and then we're going to determine the net force equations for the different scenarios. So box on the ground, that one we've done before. You can do that one. We've got a box being pulled horizontally on a frictionless surface. That's fine, kind of like A, we're going to do that. I'll do C with you. A crate being pushed horizontally across a rough surface. So if we've got a crate like so, again, it's just a box. There's nothing else happening here. So we're going to get, it's sitting on the ground, so we have a force of gravity and we have the normal force, just like so. Now, if we are pushing it, we have a force this way, which we will call FA. Now, you might be tempted to put a force like this, but you don't want this arrow going to the box. You never want your arrows in the box going towards the box. You always want that arrow going away from the box. So don't have it like that, because you see it on the left and you might think it's a negative, but it's not. The other force, because it says it's rough, When something says it's rough, that means there's friction, which means we're going to have the force of friction going in the opposite direction. So the sum of the forces in the x direction, well, if we say that to the right is positive and up is positive, then we're going to know that Fa minus the force of friction is the sum of the forces in the x direction. And very, very similar, the sum of the forces in the y direction is going to be Fn minus Fg. So there is a typical example of drawing a free body diagram and getting net force equations, some of the force equations for that, okay? Next one that I'm going to do with you is a wagon being pulled at an angle through a rough surface. On a rough surface, so we've got being pulled, we've got a tension at an angle, right? And we've got a rough surface, which tells us there's friction. Now, one thing with free body diagrams is you don't necessarily always need to draw the surface. You can literally just draw a box, okay? There's our box. Yeah, we know there's the ground here, right? But we don't need to draw it. We know that that exists. So we can just leave that out. And so instead, what we have is, okay, well, we know that there's going to be the force of gravity pushing down. And since there is surface there, we're going to get a normal force. Okay. It tells us we're being pulled by a rope at an angle, which means we are being pulled at some angle. I'm going to call it a tension, which is just our applied force. Okay. But we need to split that tension up into a Tx component, into the x component of that tension, and into the y component of that tension. Okay? Because we don't know how to deal with this purple angled vector. We need the components Tx and Ty. The last thing we're forgetting, the fact that it's a rough surface. Since it's rough, we know that there's friction opposing the motion. Okay? We know that the friction is going in the opposite direction of the applied force. Okay? Because if anything, this box is going to move to the right. We don't know if it is. Maybe friction is too strong, but if it is going to move, it is going to move to the right. So our sum of the force equations, the sum of the forces in the x direction, well, we're just going to get Tx minus the force of friction, assuming to the right and up is positive. So there we go, Tx minus the force of friction. And the sum of the forces in the y direction, a little bit fancier because now we have a Ty joining the normal force, both positive and fighting against the force of gravity. So we've got our free body diagram and then our net force equations, okay? The rest of these, I want you to try, okay? We will go over some of these questions in class. These first two are pretty straightforward. We've got somebody pushing straight down. We've got a duck suspended by two ropes, not just one rope, two ropes from the ceiling. And then we've got someone pushing down, cutting the grass on a lawnmower. If we push down, we are pushing down on the handle of the lawnmower, which means we are pushing down at an angle. Okay? So you can try that, see what that looks like. Now, these are some free body diagrams when it comes to having multiple bodies. I'm not going to go over this quite yet. You can try this on your own. I will fill in these notes so that you can actually see them. The big trick here when it comes to having multiple bodies, when you have multiple bodies, that means you must have a free body diagram for each object. You can't just do one massive free body diagram and combine the objects. You need a different free body diagram for each object. So I will explain more of this in class together. But I'd try these. We're not going to do too much stuff with multiple objects this year. Maybe in a little bit later in the unit. So it's not a huge deal. Next year, absolutely, we're going to do stuff like this. But in grade 11, we're not going to do anything too crazy. Okay. So this right here is our unit of, or our lesson of learning how to draw free body diagrams and how to work with them. In order to go forward in this course, you must be able to draw and interpret free body diagrams in your sleep. Okay, you just have to be able to do this stuff. If you can't do this, you are going to struggle mightily in this unit and into grade 12. So I really encourage you to spend a lot of time on this. Make sure you fully understand, maybe not, I don't know why I just highlighted this stuff, but really focus on this page here. Make sure you understand exactly how I'm getting these free body diagrams, where these net force equations come from, and really make sure you focus on how this all works. Because if you can't do this, we can't go forward. Okay? Awesome stuff. I will see you on Zoom.